So this is video 9. This is the video to extend 913. It's an extra credit video. It's helping us to see where the rule for an ellipse came from. It all stems from the distance formula and understanding the definition of an ellipse. And this is how they came up with this great formula, and this great quick way of graphing it was from the distance formula. So let's take a look at how this works. First, let's review the definition of an ellipse. Remember, the definition of an ellipse is a shape, a collection of points, where we have two foci, F1 and F2 in this picture, and the sum of the distances to any point on the ellipse, the sum of those two distances, R1 plus R2, is always the same, every single time. Now, let's take a look a little bit further at this picture to make a little bit more sense of what's going on here. We also want to notice that the distance of R1 plus R2 will always equal 2a. And here's why that works. Let's pick a point that's exactly in line here. Because remember, we know that the major axis is a, because we can see in this picture the distance from end to end is 2a, so the major axis is a. So let's take a look at the distance from F1 to this point, xy, or in what we know is a comma 0 in this case. Let's take a look at the distance there. So we see the distance, we know the distance from here to here is a. We also have a name for this distance, we call that c. Remember, the distance from the center to the focus is c. So the distance from F1 to that point is a plus c. Now let's take a look at the distance to F2, because we're trying to describe this distance in a simple expression. So F2, the distance to F2, well, F2 is right here, and this distance is, let's think about how we can describe that distance. Remember, the distance from the center to the edge is a, but we didn't go a, we went a little bit less than a. What's this distance here? This distance is c. So we went a minus c. That's the distance in this picture here. This distance right here is a minus c, because it's a, but take away this section that's represented with c. So F2 has a distance of a minus c. If we add these two together, we see that the distance altogether is 2a. Okay, so R1 plus R2 will always equal 2a for every point on this ellipse, because we used a general description. Now, we looked at one point on the far right. Now, the good news is it'll work for everything, because that's the definition. The sum of the distances has to be the same. So when we looked at the linear distance, the distance we can describe, we see that the answer is 2a. So let's take a look at how that helps us. We want to describe the distance for all of these points, and we know that the sum of the distances will always be 2a. Okay. A couple more things about this proof that we're doing. We're simply looking at this x0, y0 is actually going to be 0, 0. So our center is going to be at the origin. The next thing I want to remind us of is that this is a graph of an ellipse that is on the origin and has a major axis in the x direction. So that means this focus point, remember, is x minus c comma y. But in our case, y is 0. Okay, so we know if x comma c commas, it's actually negative c comma 0. Excuse me. Because we went over negative c when this was negative, which was 0. So negative c comma 0. The other focus point is at c comma 0. We didn't go up or down at all. So those are important points, because we have to use the distance formula, so we have to describe these points. So the next thing that we want to describe is this point right here. And this point is going to be described as x comma y, because we want to write a rule for those all points x comma y in this picture of the ellipse. So let's try to describe these distances. Remember, all points need to be described in this way. So we're going to take this right here, and we're going to start to convert it to x's and y's and c's and so on. So let's take a look here. R1, how can we describe this distance? Well, using the distance formula, remember we subtract the x's and we subtract the y's. So R1 can be described as the square root of, using the distance formula, x minus negative c squared plus y squared. Now the reason it's y squared is because, of course, y minus 0 is just y. That's R1. R1. We also want to describe R2. It's going to be very comparable, but instead we're going to have x minus c and y minus 0. So it'll be the square root of x minus c plus y squared. Now up here I'm going to change this minus a negative that we saw up here. I'm going to change that to just plusing a positive. So we have very similar expressions here, but they're significantly different. Now we want to add them up because we're trying to describe the sum of the distances for every point on this line. So the sum of the distance for every point on this line will be the following. The square root of x plus c squared plus y squared plus the square root of x minus c squared plus y squared equals 2a, every single point on this line. Okay, so we're at the point where we have every single point. We have a rule. We have a rule that we could use right now because remember, c and a are numbers for this particular ellipse. And we could plug in numbers for x or y to figure out what the other one is, but we want to clean this up and make it look much more easy to work with. So the first thing we're going to do is we notice that we have lots of square roots. So we are going to have to square some things, and we're going to start by subtracting this term from both sides. And rewriting our expressions here. Okay, so we take some interesting algebra. So let's see where we're headed. So once we subtract, here's what we get. Now we're going to square both sides. Of course, that's going to make the left side nice, because it will just end up with x plus c squared plus y squared. But the right side, not so nice. Okay, we have to square this quantity, which is a difference of two things. So when I think of foiling, I'm going to rewrite this maybe in two different expressions as 2a minus the square root of x minus c, plus y squared. And this will help me kind of see what I'm going to get when I FOIL. So now when I FOIL it out, it looks like I'm going to get 4a squared. The next one is going to be a negative 2a times that square root. Let's see when I do my inner. I'm going to have the same thing, negative 2a, let's see, negative 2a and a minus. So I'm also going to have that, so I'm just going to change this to a negative 4a times the square root of that quantity. And then when I times these by each other, the good news is square root times itself will equal that quantity without the square root, and it will be positive. So it'll be positive x minus c squared plus y squared. So the good news is I did clean up quite a bit of stuff, but we're not quite there yet. So let's take a look at where we're headed. And I'm going to have you pause the video and do the next steps here. I want you to clean it up. So things like the y squareds on both sides, cancel those. I want you to FOIL out this quantity, and then cancel those. Okay? And then we'll see where we're at, and we'll recheck in together. Okay, so try those steps on your own and restart the video when you're ready to see if you got the right solutions. So you should be about at this point right now. There wasn't a ton to cancel besides the x squared and y squared, which you see in red and green here. But I also kind of moved the 2cx over to the other side. And I'm even going to move the minus 4a squared to the other side. So I'm going to be ending up with 4cx minus 4a squared equals negative 4a times the square root of x minus c squared plus y squared. I'm going to continue to clean up because my end goal is to square both sides to get rid of the square root. So now I'm going to add 4a. I'm sorry, I'm going to divide both sides by negative 4a. And that's going to give me, let's see, I'm going to have the 4's will cancel here, so I'm going to end up with a negative cx over a. And then here with the other one, I'm going to have the 4s, the negatives cancel, and an a cancel. So it's going to be just plus a equals the square root of x minus c squared plus y squared. So now I can go about squaring both sides. So I'm going to square this side, and I'm going to square this side. Once again, take some time, pause the video, FOIL out the left-hand side here, and then rewrite this side with also FOILing out once you have this out of the square root. FOIL out this guy once it's out of square root. So take a moment to simplify things. You'll see my work here in just a moment. So at this point, when you FOIL it out, you see some more terms that cancel. We start to see our x squared and our y squared emerge. Now what we're going to do is we're going to get the x squared all to the right, keep the y squared on the right, and start to group things. I'm also going to move the c squared to the other side because that's my constant, and I'm going to minus this quantity and get it to the right-hand side. Okay, so let's see where I'm at. It looks like on the right, I have these two terms, on the left, excuse me, I have these two terms being subtracted. This is gone, and this is gone. And on the right, I have x squared minus c squared a squared x squared plus y squared. So this is looking a little funky, but what I'm going to do is I'm going to factor out the x squared and rewrite this as x squared times 1 minus c squared over a squared. I'm not really liking that. I think I'm going to make a common denominator. So my common denominator will be a squared. So this will end up as a squared over a squared. So altogether, this quantity here will be created to be a squared minus c squared over a squared, okay, plus y squared equals a squared minus c squared. So once again, they're not quite, mathematicians would not quite be happy with this because they don't like having, we want it cleaner. So remember what we have, our equation is a 1 on the left. So we're going to divide both sides by this quantity, but this is kind of getting messy. So what they decided was, they decided to define a new constant, and this really occurred once we realized that b comes into play. Remember, b is the length of our minor axis. So what they did is they said, let's let this quantity equal b squared. So they defined a new constant. And so what's cool is it gets rid of this guy too. He becomes b squared as well. So we now have b squared equals x squared times b squared over a squared plus y squared. And then we finish it out by dividing both sides, everything by b squared. That makes a 1. We divide this quantity by b squared, and that would cancel out this b squared, and we'd end up with x squared over a squared. And y squared over b squared, and we divide everything by b squared. This is how they derived the formula for the ellipse. Okay, it all stemmed from the distance formula, but through algebraic manipulations and defining a new constant, b, we were able to create this ellipse. And that's also why, if you remember, the c squared is related to a squared and b squared in this way. Because if we solve this equation, this variable that we defined, we'd get c squared equals to a squared minus b squared. But it stemmed from the fact that we wanted to have a simpler way to talk about that difference of those two squares, a squared and c squared. And that's where that definition came from as well. So that's an interesting take on why the ellipse formula came about. If you want to give it a shot looking at a vertically oriented ellipse. Try looking at that picture. So remember, our original picture was of this horizontally aligned ellipse. So think about turning that, having the focus is not be at c, 0 and negative c, 0 like they were here, but have the ellipse vertically oriented, now the foci are at 0, comma c and 0, comma negative c. Okay? And remember, now the a value is about a y. So every point on this, the distance between these is still 2a, but remember that it would affect what the distance formula would come about here and how you would describe any single point and r1 plus r2. So try that. See if you can do that and bring in your questions once you give that a shot. But it's just a bunch of algebraic manipulations and using the distance formula that we already defined and proved to help prove why the ellipse has this special formula of x squared over a squared plus y squared over b squared equals 1. So see if you can manipulate that and work your way to that equation for this particular ellipse. I will also be showing a video on hyperbolas in the near future so that you can also expand your knowledge on proving and explaining these formulas. So good luck with that.